We're going to get as far as we can today, and then we will keep going with this conversation. So Riemann sums are a super cool strategy. They're great. We like Riemann sums. I think they're fun. I just think sums in general are fun, but it's a great strategy for beginning to estimate the area under a curve. But we're still only estimating. We still haven't figured out an exact way to do this, because even if I did want to take like 1,000 Riemann rectangles, that's not fun to add up. And so sure, it's going to be pretty close to the exact area, but there's some challenges with that. Even if you did like 1,000 rectangles, if you wanted to know about the interval from 0 to 1,000, then your rectangles are still a width of 1, which is huge. So even if you had 1,000 rectangles, depending on how big your interval is for the area you're trying to find, 1,000 might not even be close to enough. And so if you're, in an area or an interval of 0 to 1, 1,000 rectangles is probably going to be pretty good. But you're still really only going to be estimating, because if you zoomed way in, it's a pretty shabby estimation, really, of what the exact area is, even with 1,000 rectangles. So I've alluded to, I have a secret on how to do them exact. So I'm going to finally slowly revealing my secret, step by step. Okay.
If it's going to cut our process down to like 2 seconds, I'm going to be sad.
It will.
No!
Yes.
I mean,
You should be happy.
But all the work we did previously.
Now here's the thing, we'll talk about all the work that we did previously. It was not for vain. We need to be able to still do those. We'll talk about that after I reveal my secret, but that probably won't be today. That'll probably be a conversation next week. Okay, so yeah, despite Riemann sums, they're clever, but they're not clever enough because that's a lot of computing, which is not fun or exciting. So we need a better tool. Enter the integral. The integral could be formally defined, like we talked about at the end of class on Wednesday, as a limit of an infinite number of Riemann rectangles, or the limit at infinity of a Riemann sum. So whether you use right, left, midpoint, trapezoid, doesn't matter, because if you have an infinite number of those rectangles, that's going to be the exact area. Okay, so here is the definition of the definite integral. And there it is in all her glory. It looks scary, but we know what most of this means already.
This doesn't look easier.
No, it doesn't.
I promise it is way easier. After today.
Do you mean add 2 seconds to our time?
Let's talk about the right side. This is just a Riemann sum. You finally get to know what the little squiggly is. It's here. It's the integral. So what does all this mean? We read this left side as the integral from a to b of f of x. Or you could also read it as the integral from a to b of f of x dx. The function on the inside is called the integrand. And the interval a to b is the interval of integration. It's pretty straightforward name. The interval notation, the integral in general is defined as signed area bound by x equals a, x equals b, f of x, and the x-axis. So just real quick, let me write that down. You got some function y equals f of x. Okay. The integral is defined as the signed area of x equals a, x equals b, f of x, and the x-axis. Which is exactly what we've been doing all along. It's literally not new, but this is that area is what the integral is defined as. Okay? So that's where all those pieces and parts are kind of trying to communicate. A and b is the interval of integration. It's kind of like the limit of where that area starts and ends. And then f of x would be like the top of your curve, and then obviously bounded by the x-axis. Okay, the fancy squiggle should look like that. Try to make it as accurate as you can each time. It's kind of hard to draw, but the more you do it, the more you're like, oh, that's actually not too bad. You like get really good at it. But it's really like an elongated S. And the symbol comes from, it came about because of really mathematicians' bad handwriting. Because they started hastily writing S.
For like signed area?
For sum.
For sum, okay.
Because the integral is the sum of an infinite number of rectangles. There's your height, there's your width, there's the sum of them for an infinite number of them. Okay? This is literally your right Riemann sum right here. Yeah, and then this is saying take the infinite sum of your height times your width. This is why we've been writing it as delta x, change in x. Because what does dx stand for? What have we used dx for conceptually previously? What does it mean?
Change in x.
Yeah, the change in x, specifically a very, 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 very teensy tiny change in x, right? Like just a tiny little nudge in x, yes? That's what dx is. So we're saying we're trying to make that change in x basically 0, okay? Which is basically how we were defining the derivative too, was, hey, how can I make these 2 points look like the tangent line? Oh, well, let's make that distance 0. If I'm making the width of my rectangles basically 0, and then I have an infinite number of them, gosh darn it, that's pretty much the exact area under the curve, as long as I know how to actually add an infinite number of rectangles. Okay? And that's what we need to build to. Okay, so there you go. There's the scary notation, but it's not too bad. I want you to pull out the homework packet, the signed area homework packet that you did last week. Hopefully you have that still. See if you can find that real quick. Instead of all of the words that I wrote instructing you on how to do the problems, I could have used integral notation instead as a much shorter way to tell you what to do. So we're going to practice converting the problems that I did give you in English into integral notation. So if you have that packet,
What was that?
it's the signed area one where it had the triangle, yep. It had a circle that you had to draw a circle. It had a trapezoid, had multiple triangles. I'm not sure. Oh, I did print one for me. Ah, perfect. Okay. So go ahead and look at problem 1A, and it asks you to find the signed area under the graph and bound by the x-axis from 1 to 6. Those are all the parts and pieces that you need to make an integral. And so instead of writing that entire sentence, I could have just asked you to compute the integral from 1 to 6 of, we can just call those functions f of x every time, f of x dx. Does that make sense? What would part B of problem 1 be?
Just replace the one with a 3.
Yeah, pretty much. It's gonna look all exactly the same, except I'll have 3 to 6 of f of x dx. This is telling you, find the signed area from 3 to 6 of that function, assuming that you can make little rectangles in that function. Okay? So that's all it means. It looks super scary. It literally just means those are your bounds. That's the limit of where we're trying to find the area, bound by the x-axis and the curve f of x. Okay, so how about problem 2? It says a, but there's only an a. How do you write that using integral notation?
Same thing, just replace the 3 with a 4.
Okay. Do I need to add like a negative or anything though? Since I've got negative area?
Not really. I mean, you can't really have negative area. Just leave.
We can.
Yeah.
But
We're saying you can.
Yeah. But I mean.
I guess your f of x is negative.
Okay.
True.
So I should have a negative f of x?
Maybe.
Maybe. Okay, the integral is defined as the signed area
So you
from
do
whatever
negative.
bound to whatever bound of the function. So do I need a negative if that's my definition?
Yeah.
Well, no.
I don't actually, because it's built into the assumption.
Yeah, because f of x at that point will be negative.
Yes, f of x, whatever that function actually is, like negative x, blah, 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 or whatever, already has some negatives built in. So when I actually start adding rectangles or computing the triangle area or whatever, that's already built in. So because the integral is defined as signed area, I don't need to add a negative sign, I don't need to do anything. I just need to know what the function is, or have a graph of it, and then I need to know my bounds. So I don't need a negative on that, even though it's below the x-axis. How about problem number 3? Just a.
Same thing, but 1 to 7.
Yeah, so I have the integral from 1 to 7. We'll just keep calling them f of x for now, because I haven't named any of the functions, but why did I only want to do a and not b?
Because b is total area, not net area.
Yeah.
So it's not signed area.
Right, it's not signed area, so I can't really use the integral.
Yeah.
Yeah, good. Okay, problem 4.
You put your equation in for f of x.
Okay, so what do I write?
So you've got the integral from I don't even know what you put for the integral, but
It
you
would be the sides of your circle. But I graphed it wrong, so I don't know which way it
Yeah,
goes.
so it's shifted to the right too.
is it negative
Okay.
4 to 8 or is
Yeah.
it negative 6 to 6?
It's negative 4 to 8, because we shifted it over to the right too.
Oh, okay.
Yep, so it has a radius of 6, so if it wasn't shifted, then it would be negative 6 to 6. Okay, and then what do I write? So I have the integral from negative 4 to 8.
And then you plug in your equation, so x minus 2 squared plus y squared. Would you?
Yeah, it gets weird here with the equal sign, but you're never going to have, well, okay, in Calc 1, you're never going to have any integrals that have 2 variables. So we're just gonna pretend with this one. But yes, that's the idea, is I would just put the function in. I don't need to have f of x, I can write what f of x is, which is whatever. Okay, good. We don't need to be 5a.
It'd probably just be the same thing we did earlier.
Yeah.
Just from negative 4 to 5.
Integral, negative.
Okay, so how do we say it?
The integral from negative 4 to 5 times f of x, or sorry, of f of x times.
Yep, you could just stop at f of x. You could say the integral from -4 to 5 of f of x. And you could be done. Or if you wanted to say the whole thing, the integral from -4 to 5 of f of x dx. That works great. Okay, b. How do we say it? You say it right and I'll write it.
The integral of from -2 to 5 of f of x, or of f of x dx.
-2 to 5 f of x dx. Okay, good. All right, we don't need to keep going. You got the hang of it, right? So that's good enough. And now I want us to convert between Riemann sum and integral notation. So here is the integral notation I'm giving you. The integral from 0 to 3 of x squared dx. We want to convert this information into a Riemann sum notation, and then we can compute. Okay? So I want to do a right sum with 10 subintervals. To write a Riemann sum, what information do we need?
A, B.
Well,
Which would make
Yeah, the width, which is your subinterval. Okay, so 10, and then we need A and B. So how do we find A and B?
It would be 0 and 3.
Yeah, it's actually just 0 and 3. So we label the integral, like in the definition, as A and B because it's the exact same A and B that you would have in a Riemann sum. Okay, so we need the A, we need the B, we need the N, which is your width. Do we need anything else? There is actually one more thing you do need to actually be able to compute.
you need the I.
No, you don't need the I because that's our index. It will constantly change.
Yeah.
Oh.
The function.
Yes, the function.
Which is x squared.
We need the function which we know is x squared. Good. So let's build it. R10 equals what will it equal?
3/10.
Okay.
Or, yeah.
Yep.
Mm, 10.
Uh-huh.
And then x squared, so it would be a is 0.
Mm-hmm.
So then it's just 3/10 I squared.
Yep, and if you're using I, that's
Or
fine. I use K, which is also fine. Okay, so all we really do there is we take our A, we take our B, we take our function. That gives us most of the information. The only thing that you would have to decide, or the thing that you would have to be given, is what your subinterval is, which is 10. Where do you see a 10 here?
Nowhere.
Nowhere. Why is there not 10 here?
Because it's an infinite number.
Because we're assuming infinite. Right. So I had to tell you I wanted R10 so that you knew what the subinterval was. Okay. What would it be with R1000? And then we'll go back and compute. But let's just write the notation.
Rn equals 3 minus 0 over 1,000.
Yep, R1000 over 3 minus 0 over 1,000. Yep.
That's pretty much the same thing. It'd be 1,000. Well, yeah, some 1,000 equals 1.
Uh-huh.
F of 0 plus 3 minus 0 over 1,000 k or I. Squared.
Yep. And if you write it as f of blah, blah, blah. True. But we also know what f is, so we might as well just put the squared there and okay. we're really just putting this in everywhere you would see an x in the f of x function. So if you had multiple x's in f of x, it would get a little messy, but yeah. Okay, all right, let's go back and compute this. The good news is we know some closed forms, so let's simplify a little bit. 3/10 for sure is what some of these are. So I have 3/10 times the sum from k equals 1 to 10 of 3/10 k squared. All right, think about some properties of summations. What can we do? What does it mean to be squared?
Multiply by itself.
Times itself. So I really have 3/10 k times 3/10 k, or 3/10 squared times k squared. Was it Wednesday that I gave you the properties of summations, or was that one Monday?
Something like that.
Look at your properties.
We have a closed form for k squared, or for x squared.
Okay, we do have a closed form for k squared,
Yeah.
so that's good.
Yeah.
We want to get there. Right now I have 3/10 squared k squared.
Can you just flip out?
Sure, I can do whatever I want. That's not going to help us, though.
Dang it. You said we were gonna use it sometime, Thomas.
Okay, you did
We will use all of them sometime, just not right now.
You could pull out the 3/10.
There you go. I can pull out the 3/10 squared, really.
Yeah.
So I can have the 3/10 in here is just a constant multiple. It's not dependent on the k, so I can factor it out of the sum. So I now will have 3/10 cubed out here. Times the sum from k equals 1 to 10 of k squared. Now this is good news, like Elsie was pointing out. Why do we like seeing this?
Well, we have a formula for that.
Yeah, we have a formula. Yeah, it's a closed form. So we have
N, or sorry,
3/10 cubed times,
N times,
which is 10,
times 10 plus 1, and then 210, 2, plus 1, over 6.
there you go. Okay, what does that come to? Calculate it. Have a calculator.
$10.39.
10.395. So R10 equals 10.395. That is not the exact area under the curve still. We're still estimating with 10. But now we could do 1,000. Again, good news is I'm using a closed form example, so it should go a little bit faster. If I shortcut this, do you agree that I would have 3/10 cubed times the sum of k equals 1 to 1,000 of k squared.
Should be 3/1000 cubed.
Yep, good call. Okay, now do you agree?
Yes.
Okay, good. All right, if we use our closed form again, what will that expression be?
Nine.
9.01. We actually didn't write down the answer to this one, so I'll take your word for it. I should add it to my notes. Okay, so this is fun and cool. What if you just had Rn of this same integral? Can we generalize this a little bit? .01. Okay. If we made more rectangles, what do you think it's going to go towards?
Probably 9.
Okay, maybe 9, like as the exact area. It's possible. Okay. Let's find out. We can find out. We can calculate the exact area. What do we need to do? We need an infinite number of these rectangles.
Usually.
So we need Rn,
Mm-hmm.
assuming n is infinite. It would be an expression, a formula, based on the other things that we could write.
Is there a button for the integral?
In your calculator?
Well, I mean, you just put integral from 1 to, what's the,
0 to 3.
or yeah, from 0 to 3.
Mm-hmm.
You take the limit of the sum of rectangles as n approaches infinity.
Right, so we will need, yes, the limit as n approaches infinity of this. Because really, I could back this up. Integral from 0 to 3 of x squared dx is equal to that very limit. Not as x approaches, n approaches, of Rn. Right?
Mm-hmm.
Okay, so can we come up with this formula though? We know how to calculate limits at infinity. We did that with L'Hopital's, we did that with other examples of dominance. So we could calculate that limit, but I would need a formula for Rn. I had us do these on purpose. How could we connect R10, R1000 to Rn? If I take my R1000, and if the only thing I replace here is this n, or this 1000 with an n, that would make this expression say 3 over n to the third times the sum from k equals 1 to n, because I replaced that with n of k squared. Yeah? So I will have 3 over n to the third times the sum k equals 1 to n of k squared.
Well, your first term would be approaching 0.
True.
I don't know if that helps us. So.
Yeah, so it's not helpful to us yet, but what do I know about this?
Closed form.
This is a closed form, so what will that expression be? This comes along times,
N times n plus 1 times 2n plus 1 all over 6.
there you go. Okay, we're gonna have to do a little bit of work with this to be able to calculate this limit, because we're really now gonna say, all right, what's the limit of this? Because that's what we're trying to find right here. This is the r sub n expression, but I want the limit of r sub n. So how could we simplify some of these pieces to make it easier for us to calculate that limit at infinity?
You can multiply them together.
Yeah, let's actually like do the algebra. Let's boil it out. Yeah.
I think so.
I could combine those, that would make 3n squared. Okay. All right, could we do anything else? Simplify more things? How about these ends? Can we get rid of these ends?
Good. Just cross multiply with the bottom.
I could for sure just cancel one of them straight away.
Or, since all the terms on the right side have n, just move n out.
Yep, okay, or I could factor an n. Yeah, so I could pull, do you just want to pull one n?
Could, I guess, but doesn't really do anything.
Yeah. There's a few ways we could do this. Also, at this point, I can add this, because this is really what we're trying to do. When we have a limit at infinity, what are some of our strategies? There's two main ones.
Plug it in.
Okay, plug it in. We should always check that first. What happens if I plug it in?
Your first term goes to 0, and your second term goes to infinity.
Sure, I'm going to change it like this though, because these fractions are multiplied. So they just have one fraction. So that'll eliminate the terms, but what happens then to the top and bottom? If you plug infinity in.
They both go.
Yeah.
Goes at the same degree.
Infinity over infinity. Let's use L'Hopital's rule. All right. Take the derivative of the top and bottom. This one's easy because it's just constant multiples here, so. That comes along for the ride. And that comes along for the ride. And that would give me 3n squared and 6n squared. 6n plus 1. All right, plug in infinity.
Still goes to infinity and infinity.
Yeah, I still have infinity over infinity, so
Do it again.
do it again.
Don't your 3s, doesn't your 3 cubed and your 6 turn to 0? Since,
Nope, because they are constant multiples, they're going to come along for the ride when you take the derivative.
okay.
If I was adding them, then yes. So in this case, since we're adding this one, then yes, it will. Okay, so then the 6n squared is going to make 12n, and that would make plus 6, and that would make 6n.
Still goes to infinity.
Mm-hmm.
Okay, so even when I have this, it still goes to infinity.
Yeah.
One more time. So then that would make a 6, and that would make a 12. So now I just have this as the top and bottom when I do L'Hopital's 3 times. Hopefully we did our arithmetic right. What does this come out to?
9.
Yeah, we did it right. Let's go.
Yay.
I predicted drink.
Good, Jonah.
Manifested that answer.
Good job.
You
Okay.
don't even need all this math, you just need Jonah's manifestation.
So 9 is the exact answer. It's true that 9 is the answer here. And really what we did was use our closed form of a Riemann sum to find the exact area. Crazy. That's super cool. Use our L'Hopital's rule, our closed forms, our Riemann sums, derivatives, all of it comes together and is helping us to be able to calculate the exact area. Amazing. Okay, good. So,
It did turn out to be useful.
it did turn out to be useful. Yep. I promise it gets faster and faster. Let's do this. What?
That did not take 2 seconds.
Oh, it's because I still haven't told you the secret.
No.
We're still getting to the secret. Don't worry.
You can't keep me in suspense.
It's gonna be, I think, Monday, depending on how far we can go today. Number 7 through 10, with haste, page 355. Let's make it happen. If I remember right, this is a graph, and we need to find R3, L3, M3, T3 for 7, 8, 9, 10.
No, it did technically take shorter than if we had to add up an infinite amount of.
Yeah, that's true.
That's facts. That's facts. Okay, yes, I was right. It is a graph. There you go. Okay, fun fact, you have homework problems on this very graph.
Oh.
So, good thing we're doing these in class so you know how to do your homework. Okay. How kind am I?
Super.
So,
Oh, thank you, thank you.
Except when you hold us in suspense for over
When you
4
keep-
days.
keeping secrets.
I promise you this is the very last secret I'm holding from you for all
You
of
promised
calculus.
the last secret.
I promise that it was the last derivative secret I'm holding from you.
How can we trust you anymore?
This is the very last secret I will hold from you for all of calculus. 1. No!
I told you.
For calculus 1.
Was puppy.
I like to keep secrets too, so it would be fun if I have other secrets. Okay, so number 7, estimate the value of the integral from 1 to 7 of f of x dx using a right sum with 3 equal subintervals. So here we're going to have to actually calculate R3 using this graph, because we don't actually know what the function f of x is. But we could find some of those values on the graph. So from 1 to 7 is where we want to find that area, and it's asking us to use 3 equal subintervals. What will those subintervals be?
1 to 3, 3 to 5, 5 to 7.
Yeah, there you go. 1 to 3, 3 to 5, 5 to 7. And because it's a right sum, so this is really R3, where will that endpoint be in each of those subintervals? Do you know?
Where would the end come?
Yep.
So like if we're using a right side, where does that vertex go?
Yeah, where does that,
Or not vertex? What am I thinking of?
Endpoint.
I mean, versi is how you would call it, but yeah.
It would go on 3, wouldn't it?
On 3, one of them is 3.
Well, yeah.
How about for all of them? For all those intervals, where will that right endpoint be? One of them is at f of 3.
Mm. The other one is at f of 5. The other one is at f of 7.
Good.
So
So, if I make my Riemann sum here, it would be b minus a over n, 7 minus 1 over 3, times f of 3 plus f of 5 plus f of 7, right? Okay, that's not too bad. We can calculate that. What's f of 3?
3.
Yeah, 3. And then, so 7 minus 1 over 3 is 2. And then f of 3 you said is 3. Okay, f of 5.
6.
And then f of 7.
3.
There you go.
Do we have to times it by their base though?
Hmm?
Their width.
Yep, I'm multiplying by the width right here.
Oh, yeah.
Boop, there's the width on each of them. 3 plus 3 is 6. 6 plus 6 is 12. 2 times 12 is 24. There we go. So now again, we're practicing converting that integral notation to the Riemann sum. We're making those connections. So how about number 8? We want a left sum with 3 equal subintervals. That width will be the same. It'll still be 7 minus 1 over 3. And then what will my f values be this time?
1, 3, wait, yeah, 1, 3, 5.
Yeah, f of 1, f of 3, and f of 5. All right. What's f of 1?
6, okay, 5.
5, and then f of 3, we already know is 3, and f of 5, we already know is 6, because we just did those up here. What does that come out to in the total? I got to. Okay. Array 9 is just asking us to do M3, M sub 3. So we'll take that midpoint sum. So the width is still 2, because I still have 3 equal subintervals. But what will those f values be?
F of 2, f of 4, f of 6.
Yeah, we'll need f of 2, f of 4, and f of 6, which is 3, 6, and 5. Something that's interesting about the AP exam is if you leave this as your answer, that's 100% correct. You don't have to simplify or arithmetic. So you would really be done at that point. But if you wanted to find the actual value, we could simplify it and it would be
28.
also 28. Yep. Okay, number 10. A trapezoid sum T sub 3. Good news is we've done the hard work. We just need to take R3 and L3, divide by 2. What is the average value of 24 and 28?
26.
Good. 26. Good. Okay. Nice. This is what those homework questions will feel like. Those are the ones I said you're not going to know how to do this until I talk about it on Friday. Now you know. Because it's 11, 12, 13, 14. Okay? Any other homework questions with our last 2 minutes? Did you get started on it at all? Maybe you didn't start. That's fine. Okay.
I did the first part, and then it goes into that.
It's due on Wednesday. So you still have this weekend and Tuesday to keep working on it. I don't want to get started on the next one because we're not going to have time to finish it. So we will do that on Monday. But you guys are rocking this. This is pretty good. This is what we will do on Monday if you want to like get that started at least and like write it down. But save yourself the time on Monday. Good job. We're gonna do a few more examples on Monday. Let's see. Two that are like really fast, and then this one which isn't hard, it just takes a long time to write it, but we got it. And then I will connect some more things. Hopefully by the end of Monday we'll get to my secrets. We'll see. For sure Wednesday, like guaranteed.
Okay.
Maybe Monday if we can like lock in. Okay.
My trust has been all